Hello my friends and welcome back to the You Can Do TV channel. This overview details the production of 17 units of heavy-duty 2-axle rigid dump semi-trailers, emphasizing the various steps and components involved from start to finish. Base frame production. The foundation of the trailer is the base frame, consisting of 2 heavy steel beams. These beams are integral to the structural integrity of the trailer. The production of the base frame begins with the careful selection of high-strength steel, followed by precise cutting and welding to form the main skeleton of the trailer. Ensuring accurate alignment and secure welds is crucial, as any deviation can compromise the entire build. Main frame assembly. Once the base frame is constructed, the next step is assembling the complete main frame, which includes the installation of the kingpin. The kingpin is a pivotal component that connects the trailer to the towing vehicle, and its proper placement and securement are vital for safe operation. The main frame assembly also involves the integration of cross members and reinforcements to provide additional strength and rigidity. Surface preparation, sandblasting and priming. With the main frame assembled, it undergoes sandblasting to remove any rust, scale, or impurities from the metal surface. This process ensures a clean and smooth surface, which is essential for the primer to adhere effectively. After sandblasting, the frame is primed to protect it from corrosion and to provide a base layer for the final paint. Trailer body production. The production of the trailer body is a detailed process involving numerous steps and considerable craftsmanship. Each component of the trailer body is fabricated, shaped, and assembled with precision. Professionals with expertise in metalwork and assembly are required to handle this phase, ensuring each part fits perfectly and performs its intended function. Assembling the trailer body. Assembling the trailer body involves the integration of various components, such as the sides, floor, and front and rear panels. This phase requires detailed work and attention to alignment and secure fastening. The bracket for the movable rear wall, an essential feature for dump trailers, is installed during this stage. This bracket allows the rear wall to pivot, facilitating the dumping process. Surface treatment, degreasing, priming, and painting. Before the final assembly, all components undergo degreasing to remove any oils or contaminants that could affect the paint adhesion. Once degreased, the parts are primed and painted. This not only enhances the appearance of the trailer but also provides additional protection against the elements and wear. Final assembly. Mounting the rear hatch and axles. The final assembly includes mounting the rear hatch, which is crucial for the dumping functionality of the trailer. BPW heavy-duty W axles with Trilex rims are then installed. These axles are designed to handle the significant loads and stresses that come with heavy-duty operations. The trailer body is securely connected to the main frame using 136 bolts, ensuring a robust and durable connection. Preparation for transport. Once the trailers are fully assembled and inspected for quality and safety, they are prepared for transport. This includes securing all components and ensuring the trailers are ready for shipment. The final destination for these trailers is a German seaport, where they will be transported to their respective end users. The Hitachi X1200, featuring a 30-meter long arm boom, is a highly specialized piece of equipment designed for demanding dredging applications. This impressive boom is constructed using SSAB Strenx 700 structural steel, chosen for its exceptional load-bearing capabilities and durability. The manufacturing process of this advanced equipment involves a series of executed steps to ensure maximum performance and reliability. The first step in the manufacturing process is steel cutting, where steel plates are precisely cut to the required dimensions. Following this, steel plate chamfering bevels are created to prepare the edges for welding. This chamfering is crucial for achieving strong welds and maintaining structural integrity. Next, the assembly stage begins. The pre-cut and beveled steel plates are carefully aligned and held in place. Auto welding is then employed to join these components. Automated welding ensures consistency and precision, essential for the structural soundness of the long arm boom. Once the main structure is welded, boring holes is performed. This step involves creating precise openings for later assembly stages, such as the installation of hydraulic pipes and other components. Following hole boring, final welding is completed, ensuring all parts are securely and accurately connected. A critical quality assurance step is the SGS welding inspection. This non-destructive testing process verifies the integrity and strength of the welds, ensuring they meet stringent standards. After passing the inspection, the boom undergoes sandblasting. This step cleans the surface, removing any impurities and preparing it for painting. Installing pipelines is the next phase, where hydraulic and other necessary pipelines are integrated into the structure. These pipelines are essential for the boom's operational functionality, allowing it to perform its dredging tasks efficiently. The final steps include premier painting. The boom receives a coat of high-quality paint, which provides both aesthetic appeal and protection against corrosion and environmental factors. The 3.4 cubic meter rock bucket for the Komatsu WX07 is built to withstand the rigorous demands of underground loading operations, featuring a high-strength construction and an array of protective features. The production begins with the selection of high-strength, wear-resistant steel plates, which form the foundation of the bucket structure. These plates are meticulously cut and shaped to the bucket specifications using advanced CNC machines, ensuring precision and consistency. The steel is chosen for its durability and ability to resist the abrasive nature of rock handling. A key component of the bucket is the mechanical ground engaging tools, GET, lip assembly. This assembly includes replaceable teeth and adapters, which are critical for penetrating tough materials and protecting the bucket lip from excessive wear. The mechanical design allows for easy replacement and maintenance, extending the bucket's operational life. In addition to the GET lip, the bucket is equipped with a full mining wear package. This package includes heel shrouds and interlocking profile bars, which provide additional protection to the bucket's most vulnerable areas. Heel shrouds shield the bottom rear corners of the bucket from impact and abrasion, while interlocking profile bars add structural integrity and reduce the risk of material hang-up. Throughout the manufacturing process, Rigorous quality control measures are in place to ensure that each bucket meets Komatsu's high standards. Welds are inspected using non-destructive testing methods, and the final product undergoes a thorough examination to verify its readiness for operation in challenging mining environments. The result is a robust, 3.4 cubic meter rock bucket that enhances the performance of the Komatsu WX-07 underground loader. Its design and construction ensure longevity, reliability, and efficiency, making it an essential component for mining operations requiring heavy-duty material handling. Komatsu's UK operation is part of the extensive global Komatsu organization, the world's second-largest manufacturer and supplier of construction and mining equipment. Based in Tokyo, Komatsu oversees 140 companies worldwide and operates around 40 manufacturing plants, employing approximately 47,000 people globally. The UK facility, officially opened in 1987 by HRH the Prince of Wales, is located in Chester-le-Street and employs around 400 staff. These employees produce 17 models of Komatsu excavators, which are exported to Europe and North Africa, in addition to serving the UK market. Visiting a construction machinery manufacturing facility is always an engaging and enlightening experience, one that remains captivating even after numerous visits. A particular highlight of visiting Komatsu is the lack of restrictions on photography in and around the plant. This openness reflects their confidence in the quality of their work as machines progress down the production line. The plant features state-of-the-art robot welding machines, some of which were busy welding undercarriage sections during the visit. These machines, likely destined for customers in Central Europe, are often painted in the company's distinctive corporate colors. A dark gray machine with a tab boom was nearing completion, while at the start of the line, a base upper structure painted silver was beginning its assembly, set to be matched with similarly colored components further down the line. The assembly process includes lifting the completed upper structures and joining them with the undercarriages. Once everything is connected and plumbed, the machines are capable of moving under their own power down the line. After assembly, the machines undergo testing on the Dynamic Evaluation System, DEI, a test bed where they are locked down and operated for a specific period to check for leaks or other issues. Machines are then tested in operation in another area of the factory before undergoing a final inspection. Once cleared, they are moved to the yard area for storage and dispatch. Mounting the track roller, assembly line of track frames. Mounting the swing circle. Mounting the final drive. Mounting the idler. Mounting the swing circle and greasing. Mounting the crawler. Mounting the main valves. Mounting the hydraulic oil tank. Mounting the engine. Attaching the exterior parts. At the Komatsu plant in the UK, they manufacture for Europe medium-size and large crawler excavators, 18 to 70 tons, including excavators equipped with intelligent machine control technology. Watch the video and enjoy the Komatsu way of manufacturing at the Osaka plant for the production of the PC200 excavator. Main assembly line. Docking. Research and development. Mounting the swing machinery. Mounting the arm. Attaching the counterweight. Attaching the bucket. Mechanical performance inspection. Factory shipment inspection. Factory shipment and delivery. We're in the body shop at Ford's Sannon plant. Here a Ford is built tough. Durable sheet of metal are put together using advanced equipment to shape and join the pieces. The workers take care of cars through a meticulous painting process, carried out entirely by robots. The 5 layers of paint don't just look good, they protect the car too. This part shows a peek into the engine department at Ford's Sannon plant. Ford engines are built to last, like a family does. They put them together with every care and then scan and inspect them repeatedly. The construction process of GM trucks involves several steps, including the design and engineering of the vehicle, the manufacturing of the individual parts, and the assembly of the final product. The body is typically made of high-strength steel, with various components such as the engine, transmission, and suspension system assembled and installed onto the frame. The General Motors (GM) paint process is a highly controlled and precise system that ensures that each car receives a high-quality paint finish. Every surface must be meticulously cleaned to remove any debris or contaminants that could compromise the quality of the paint job. After the car has been thoroughly cleaned, it goes through a pre-treatment process. This process involves the application of a chemical solution that further cleans the surface and prepares it for the next step of the paint process. Next, the car enters the E-coat primer phase. In this phase, the car is submerged in an electro-deposition coating tank. The primer acts as a protective barrier against rust and corrosion. After the E-coat primer phase, the car is baked in an oven to cure the primer. At the manual inspection deck, experts visually examine the car to ensure that there are no defects in the primer. If any issues are identified, they are immediately addressed before proceeding to the next step. The next step is to make all seams watertight to keep water, fumes, and noise out of the truck. Fort Wayne Assembly's paint shop uses many robotic body seal cells. In the final cell, liquid applied sound deadener, LASD, is applied to give each truck a quieter ride. At this point, the truck enters the anti-chip cell, where robots spray a special coating onto the lower box sides. rockers, and fenders to protect the finish from chips thrown up from road surfaces. Now, the trucks are ready to be primed. This primer offers UV protection for long-term durability and color code adhesion. Once the primer has been applied, the truck body is sent to a split oven for its second baking. At this stage of the paint process, each truck body is sent to the moist sand prep deck. Each truck is once again dusted with ionized ostrich feathers to ensure a clean surface for the paint to adhere. Fort Wayne Assembly has 10 paint modules, each with the capability to spray every color available on Chevrolet and GMC trucks. Each paint module has its own oven that sets and cures the freshly painted trucks, providing an efficient, high-capacity paint shop to keep pace with our customers' orders. Afterward, robots apply a clear coat for extra protection and shine. Once again, the quality control team carefully inspects the new coating for any inconsistencies. When satisfied, the team sends the truck through a final baking process. Upon leaving the final paint oven, the truck travels to the finesse deck, where a complete team of inspectors performs a series of visual and manual quality checks on each truck to ensure it is defect-free before leaving the paint shop. The Lexus NX is produced at the Miata plant in Kyushu, Japan. The all-new Lexus NX breaks the mold. It's the first Lexus compact crossover SUV, and the first Lexus vehicle to offer a turbo model. The NX combines sporty urban driving performance with the power of an SUV. Two variants, the NX200T, the first Lexus fitted with a turbo engine, and the NX300H, powered by a hybrid system, both offer responsive, engaging drives and excellent environmental performance. This plant's trailers are renowned for their robust quality, functionality, and durability. These attributes have earned the company certifications as an upper structure supplier for major corporations like 4.07 and BMC Incorporation. The company maintains a 12,000 square meter stock area, secured 24/7, where vehicles await their upper structures, ensuring their safety and integrity. The manufacturing begins with cutting the trailer chassis and other parts using computer-aided CNC machinery. This precision ensures high-quality components ready for assembly. The company uses certified materials such as Hardox Domex, Daco ST52, ST44, and SD37 iron plates, sourced from reputable suppliers. Additionally, direction control walls, limit control walls, and palms are integral to the production process. Full-type dumper trailers and Hardox 450 wear plates from SSAB are employed for enhanced durability. Special metal processing and vending machines handle wear plates with a hardness of 450 perennial and a thickness of 12 millimeters. Iceland dumper stocks wear plates ranging from 3.2 millimeters to 150 millimeters, ensuring availability for various production needs. The preparation crew creates specific parts, which are then carefully assembled by the installation crew. Upper structures, designed under the trademark of Z Aslan, are produced in automated modes, adhering to mass production standards. Hydraulic systems are installed in the trailers, followed by thorough inspections and tests. Quality control and project follow-up are conducted at every production stage by the technical crew. The plant specializes in producing tipper trailers suitable for transporting light excavation materials and pallets. These trailers are designed with reinforced profiles and extensions to ensure durability and functionality. The tipper trailers feature a 4-sided cover with 60 cm reinforcement in the supporting profiles. The extensions are hinged, and the supporting profiles are one-row nesting type. The upper chassis is made of NPU 140 and reinforced with 6 mm Street 44 steel. The dimensions of the tipper trailer are as follows. The inner length is 8,300 mm, the inner height is 1,000 plus 350 plus 350 mm, and the inner width is 2,400 mm. The materials used include a floor thickness of 3 mm Domex, a front wall thickness of 2 mm Street 37 steel sheet, side walls thickness of 1.2 mm Docal, and a tailgate thickness of 2 mm Street 37 steel sheet. The extensions are made of 2 mm Street 37 steel sheet. The chassis frame is made of 5 mm thick Domex steel in an I construction. The cutting-edge dimensions are 120/12ths of a millimeter, 120/14ths of a millimeter, and 120/16ths of a millimeter. The trailer features a 2 inches kingpin compliant with DIN and SAE standards and a 25-ton dynamic and 50-ton static mechanical landing gear. The rear bumper meets EEC 97/19 standards. The axles have a capacity of 12 tons each, equipped with brake shoes and heavy brake levers, and dual lifting axles. The suspension system comprises parabolic double-deck Z-springs. The tires and rims are 385/65 R 22.5, 6+1, and 11.75 by 22.5, 6+1, respectively. Before painting, the trailer bodies are cleaned with special chemicals and sandblasted to remove waste materials. The surfaces are then coated with a 2-coat epoxy primer and a 2-coat water-based paint, applied in a modern painting cabin. Standard accessories for the trailers include mud guards, mud flaps, toolboxes, plastic saddles, spare tire conveyors, tarpaulin hooks, reflectors, water tanks, ladders, and sidebars. Each product undergoes rigorous quality control to ensure compliance with worldwide standards and customer satisfaction. The hydraulic system includes a 5-stage heavy-duty cold-drawn telescopic cylinder, a hydraulic oil tank with a capacity of 150 liters, a dual-speed download valve, a limit check security valve, and a 35/85 dpa gear pump. The braking system is a twin-line air brake system compliant with EEC 98/12 standards, featuring EBS, 2S, 2M sensor, and roll stability support, RSS. The electrical and lighting systems comply with SAE standards and TÜV regulations, powered by a 15-pin socket, EEC 97/28, or 2x7-pin socket, ISO 12098, with brake lights, number plate lights, yellow side lights, and a fuse box. This section shows Mita's Tires factory and explains how tires are produced, highlighting each stage in detail. Extruding and calendering. The first stage in tire production involves the creation of various rubber components. After mixing the rubber compound in a laboratory and ensuring it meets quality standards, the rubber is formed into sheets. These sheets are then processed through extruder machines to create the tread and sidewall components. Calendering is used to produce the inner liner. The extruders produce continuous sheets of tread rubber, which are then cooled and cut to specific tire lengths. Rubber coating. The mixed rubber compound is used to coat sheets of cords, such as nylon, polyester, and steel, on both sides. These coated sheets are then cut at the correct angle, which determines the tire's characteristics. These sheets are crucial for casing belts and other plies. Bead wire. Bead wires are made by aligning and coating steel wires with rubber. These coated wires are then wound into coils to form bead rings. The number of loops and the shape of the bead wire are specific to each tire's design. Tire building. At this stage, all the tire components are assembled. Tire building begins with the sidewall and rim strip, followed by the bead lining, inner liner, and 2 carcass plies. Bead cores are placed on the building drum, and the ply edges are wrapped around the bead core. The sidewalls are then moved into position, and the tire is reshaped. After inflation, belts and tread rubber are applied, creating a green tire that closely resembles the final product. The difference between radial and bias ply tires. There are 2 main types of tires: older bias ply tires and newer radial ply tires. In bias ply tires, the cord is laid at an angle of 60 degrees relative to the tire's movement, forming a crisscross pattern. In radial ply tires, the cord in the casing ply is laid at a right angle to the center of the tread. Radial ply tires are more complicated to produce but offer benefits such as fuel efficiency, longer lifespan, improved comfort, and reduced soil pressure in the case of agricultural tires. Curing. After tire building, green tires are cured in a process called vulcanization. The green tire is covered with a solution that helps it fill the mold. It is then placed in a curing press where heat and pressure are applied. The heat causes the rubber compound to become plastic and fill the mold. Vulcanization occurs as the polymers in the rubber are linked by sulfur, creating a 3-dimensional pattern of interlinked polymers. The curing process gives the tire its final shape and characteristics. The duration of curing varies, with passenger car tires taking only a few minutes and agricultural tires requiring up to 2 hours. Before leaving the manufacturing plant, each tire undergoes finishing and final inspection. This involves trimming the tire to meet specific requirements and conducting visual inspections for surface defects. Testing machines measure central and lateral runout compliance with industry standards. Tires containing steel cords are inspected by X-ray for internal defects. The final inspection ensures that each tire meets quality and safety standards before it is ready for dispatch to customers. Tire retreading is a sustainable and cost-effective solution that extends the life of tires, reducing waste and operating costs for fleets. In this part, we will explore the intricacies of the tire retread process. The initial inspection serves as the cornerstone of the tire retreading process. Its primary objective is to assess the condition of the tire casing and determine whether it is suitable for retreading. Visual inspection involves a thorough examination of the tire's external surfaces. Technicians meticulously search for visible defects, including cuts, bulges, punctures, and separations. They also inspect the sidewalls and bead areas for any signs of damage. Additionally, electronic detection tools, such as ultrasound or X-ray scanning, may be used to uncover internal structural damage that might not be visible to the naked eye. The outcomes of the initial inspection determine the tire's fate. If the casing passes the inspection and is deemed suitable for retreading, it proceeds directly to the scraping process. However, if the tire is found to be beyond repair or not suitable for retreading, it is returned to the customer. Scraping process. This step involves the meticulous removal of the old tread and any residual debris from the tire casing. The goal is to create a clean, properly contoured, and texturized surface on the casing, ready to receive the new tread. Highly specialized buffing machines are deployed for this critical task. These machines are designed to carefully strip away the worn-out tread, ensuring that the underlying casing remains undamaged. As technicians guide the tire through the buffing process, they pay close attention to hidden defects that may be lurking beneath the surface. Objects like sharp rocks or glass embedded in the casing are discovered and promptly removed, and any structural issues are addressed. The scraping process is fundamental to the retreading process, as it ensures that the casing provides a suitable foundation for the application of the new tread. It also serves as an opportunity to identify and rectify any previously undetected defects that could compromise the tire's integrity and safety. The reaming process is a crucial step that contributes to the successful adhesion of the new tread to the prepared casing. This procedure involves the use of specialized reaming tools that create a rough texture on the casing's surface. The rough texture generated by the reaming process enhances the casing's bonding potential. It provides an ideal surface for the cementing process that follows, ensuring that the new tread securely adheres to the casing. This step, often overlooked by those unfamiliar with the retreading process, is essential for the long-term performance and safety of the retreaded tire. Cementing process. During this phase, a bonding agent or cement is applied to the casing's surface. This cement serves as the adhesive that facilitates the secure bonding of the new tread. Highly skilled technicians carefully apply a layer of cement to the prepared casing, ensuring that it covers the surface evenly and consistently. After the application of cement, the casing is allowed to cure for a specific period. This curing time is crucial, as it allows the cement to reach the desired level of tackiness for tread application. The cementing process sets the stage for the next step, where the new tread will be applied to the casing. Filling process. The filling process is essential for achieving the desired contour and shape on the casing before the new tread is applied. This step may involve the addition of cushioning or filling materials, depending on the tire type and specific requirements. Technicians carefully evaluate the casing's shape and may use extruded rubber cushion or other appropriate materials to fill in gaps and create a smooth, even surface. Ensuring the proper contour is critical, as it sets the stage for the secure adhesion of the new tread during the subsequent building process. The building process is a pivotal stage in the intricate journey of transforming worn-out tire casings into reliable, high-performing retreaded tires. It represents the point at which the new tread is meticulously applied to the prepared casing, creating a retreaded tire that adheres to stringent quality and safety standards. The significance of the building process. The building process holds a central position in the tire retread cycle. It is where the tire's functional heart, the new tread, is fused with the prepared casing. The key objectives of this phase are precise alignment, ensuring that the new tread aligns accurately with the desired tread pattern and specifications, as per the tire's intended purpose and performance requirements. Uniformity. Achieving uniformity in the tread width, design, and composition to meet customer specifications and industry standards. Bonding. Establishing a strong and enduring bond between the new tread and the casing, vital for safety and performance. Tread splicing. If required, in cases where the tread material comes in long strips, technicians must meticulously splice and join the ends to attain the desired tread circumference. Craftsmanship. The building process demands a high level of craftsmanship, precision, and attention to detail to ensure that the resulting retreaded tire is safe, reliable, and fit for purpose. Procedures in the building process. The building process is executed with meticulous care and precision. The following steps outline the procedures involved. Tread application. Highly skilled technicians apply the new tread to the prepared casing. This step is a delicate dance that requires exacting attention to detail. The technicians ensure that the tread aligns precisely with the desired tread pattern and specifications. The specific tread width, design, and composition are selected based on the tire's intended purpose and performance requirements. Tread splicing. If required, in scenarios where the tread material comes in long strips, the technicians must splice and join the ends to achieve the desired tread circumference. This operation involves carefully matching the ends of the tread material and creating a secure bond. The precision of this step is essential to ensure the tread's integrity and uniformity. Uniformity check. Technicians meticulously inspect the tread application to verify that it adheres to the required specifications and standards. Any deviations from the prescribed dimensions or design are addressed to maintain uniformity. Bonding. Ensuring a strong and enduring bond between the new tread and the casing is paramount for safety and performance. Technicians utilize the preparation work done during the initial inspection, scraping, reaming, and cementing processes to achieve optimal adhesion. Quality assurance. At every step, technicians conduct quality checks to confirm that the tread application meets the highest standards of workmanship. Any irregularities or imperfections are addressed promptly. Craftsmanship. The building process demands a high degree of craftsmanship, as even minor discrepancies in tread alignment or bonding can impact the tire's safety and performance. Technicians take pride in their role as tire artisans, ensuring that each retreaded tire emerges as a meticulously crafted product. Statistics on the number of retreaded tires. The practice of retreading tires has a significant impact on the tire industry and the environment. It is a sustainable solution that extends the life of tires, reduces waste, and contributes to cost savings for fleet operators. While the exact number of retreaded tires may vary from year to year, retreading remains a prominent industry practice. Here are some key statistics on the number of retreaded tires. Global retread market size. The global retread tire market size was estimated to be around 150 million units annually, with varying figures depending on the source and year. This figure highlights the substantial scale of the retread industry. North America. North America has been a significant market for retreaded tires, with an estimated retread market size of around 30 million units annually. It's a region where retreading plays a critical role in optimizing the life cycle of commercial truck tires. Europe. The European retread market is also robust, with countries like Germany, the UK, and France having substantial retreading operations. The region contributes significantly to the global retread tire market. Asia-Pacific. The Asia-Pacific region has seen growth in the retread market, driven by the expansion of commercial vehicle fleets. Countries like China and India have witnessed increased retreading activity. Environmental impact. Retreading reduces the demand for new tire production, resulting in reduced resource consumption and lower carbon emissions. The practice aligns with sustainability goals, making it an environmentally responsible choice. The wrapping process is a crucial element of the packing phase, where the protective envelope or wrapping is securely fastened around the retreaded tire. This step is vital in ensuring that the protective covering remains in place, providing continuous support and protection. Technicians take great care to secure the wrapping tightly, leaving no room for movement or shifting during the curing process. This meticulous attention to detail safeguards the retreaded tire and preserves the integrity of the new tread's bonding with the casing. The autoclave is the heart of the curing process, where the retreaded tire undergoes a controlled curing procedure to establish a strong and lasting bond between the new tread and the casing. One of the key mechanisms employed during curing is enveloping. A rubber membrane or envelope is placed around the tire, encompassing it from bead to bead. This envelope serves a vital role by creating a pressure differential between the inside of the casing and the outside of the tread. This pressure differential ensures that the new tread adheres securely to the casing, creating a strong and reliable bond. The final verification step is a crucial quality control measure that takes place before the retreaded tire is returned to service. Technicians conduct a thorough inspection of the retreaded tire, checking for various critical factors to ensure its quality and safety. The process of remolding a tire is a meticulous and eco-friendly approach to extending the life of used tires, reducing waste, and providing cost-effective alternatives to consumers. The first step in the remolding process begins with the selection of high-quality, used tires that are suitable candidates for remolding. Each tire selected for remolding is assigned a unique serial number. The serial number is recorded in a database, ensuring that every tire can be tracked from the initial selection to the final product. Checking tire dimensions. Before remolding can begin, the dimensions of the tire are carefully checked to ensure they meet the manufacturer's specifications. Buffing. Roughing the surface. The old tread and any imperfections on the tire's surface are removed through a process called buffing or roughing. This step creates a clean and even surface for the remolding process. Wrapping the sidewall protection. A protective layer is applied to the tire's sidewalls. This layer helps protect the tire and provides added durability and resistance to wear and tear. Wrapping, building up tread. A new layer of tread rubber is applied to the tire's surface. This is carefully done to create the desired tread pattern and thickness, ensuring optimal traction and performance. Molding, pressing the green tire. The tire, now with its new tread and protective layers, is placed in a mold and subjected to heat and pressure. This process is crucial for curing the new tread and bonding it securely to the tire's casing. The result of this meticulous process is a remolded tire that not only extends the life of a used tire but also offers performance and safety comparable to a brand new tire. A semi-automatic tire building machine plays a pivotal role in the tire manufacturing process by assisting workers in creating the foundation of a high-quality tire. This sophisticated piece of equipment combines human expertise with precision engineering to ensure that every tire is built to exact specifications. The tire building process begins with the worker wrapping rubber around a drum body. This initial step is critical, as it sets the foundation for the tire's structural integrity. The worker carefully places layers of rubber onto the drum body and meticulously folds the edges of both ends. This step requires a high level of skill and precision to ensure that the rubber is evenly distributed and free of defects. Once the base layer is in place, the semi-automatic tire building machine takes over. It continues to wrap additional layers of rubber onto the drum body. These layers consist of various components, including inner liners, steel belts, and tread compounds, depending on the type of tire being produced. The machine's automation ensures that each layer is applied with consistency and precision, eliminating the risk of human error. One of the key features of the semi-automatic tire building machine is the roller system. This system consists of rollers that press and smooth each layer of rubber as it is applied to the drum body. The rollers play a crucial role in ensuring the perfect adhesion of different carcass ply layers. This is of utmost importance in tire manufacturing because it directly affects the tire's performance, durability, and safety. Perfect adhesion between carcass ply layers is essential to prevent delamination, which occurs when the layers of a tire separate from each other. Delamination can lead to tire failure and pose a significant safety hazard. The roller system on the tire building machine exerts consistent pressure, smoothing out imperfections and air pockets between the layers. This results in a tire with excellent uniformity and structural integrity. Furthermore, the roller system helps to evenly distribute the rubber compound, ensuring that the tire's weight is balanced. This is vital for reducing vibrations and providing a smooth and stable ride for the vehicle. Balanced weight distribution also extends the tire's lifespan and improves fuel efficiency. Preparing to manufacture brand new tires. Inserting rubber-coated steel wire for reinforcement. The foundation of a new tire begins with the insertion of rubber-coated steel wires, which provide the tire with structural integrity and reinforcement. Building up, wrapping the hard, base, portion of the tire. The base portion of the tire, made of a specialized compound, is carefully built up or wrapped around the steel wire reinforcement. This layer forms the tire's inner structure and contributes to its overall strength and stability. Molding, pressing the green tire. The tire, in its green or unvulcanized state, is placed into a mold. Heat and pressure are applied to shape the tire into its final form, including the desired tread pattern. This vulcanization process chemically bonds the rubber compounds, making the tire durable and resilient. The result of these meticulous steps is the creation of a brand new tire. These tires are known for their consistent quality, safety, and performance, meeting stringent industry standards. Car manufacturing begins with the creation of doors, hoods, and other body parts from large steel plates. One car can use more than a dozen types of steel plates. The steel plates are fed into a cutting machine and punched into different shapes and sizes. They are then pressed into the shape of parts in a process that takes only 3 seconds, applying 1,600 tons of pressure to make each part. Next, the shaped parts are put together in the welding area, where the car's body takes form. First, the floor, sides, and ceiling are assembled, with as many as 4,000 welds performed to ensure high precision and stability. Following welding, additional parts like the doors, hood, and trunk door are attached to the body. An inspector then uses a human touch and visual checks to confirm quality. The paint process begins with a wash, an important step for the subsequent layers of paint. The first step is the primer process, where the body is dipped into a pool of rust-resistant paint. Sealer is then applied to the steel plate joints. Next, the body is prepared for the middle coat, a crucial step for achieving a beautiful color. The top coating process follows, with each car painted one by one in its designated color. Finally, a clear coat is sprayed to add luster. Once the car body dries, inspectors rigorously check the painted surface. Parts installed here come from the cooperation of more than 100 parts suppliers in addition to Toyota's own plants. As many as 3,000 parts are installed along a line more than half a mile long. To create space for work, the doors are temporarily removed. Interior components such as electrical wiring and the ceiling liner are installed, followed by the engine, brakes, and other undercarriage components. Then, bumpers, tires, seats, windshields, and rear glass are installed. Finally, the doors are reattached. Once assembled, inspectors confirm that the correct parts are installed and check for any scratches or dents. They then inspect and adjust the lighting fixtures, gauges, and check for any unusual noises, confirming the effectiveness of the gas and brake pedals. Finally, inspectors check for oil leaks. Only vehicles that have passed all of these rigorous inspections are delivered to customers. This meticulous process is done every day for each and every vehicle shipped domestically and throughout the world. The BMW safety facility features an advanced rollover testing program that exceeds the requirements of the United States National Highway Traffic Safety Administration. BMW's philosophy on safety is focused on three tests: the corkscrew, Gaza sandpit, and embankment test. These tests simulate real-life scenarios where a vehicle may experience a rollover. BMW has equipped the new X6 Sports Activity Coupe with rollover sensors that can detect angular rate and acceleration to deploy the head protection system and seatbelt pretensioners in the event of an imminent rollover. The embankment test proved to be one of the most challenging for the X6 due to its low center of gravity. Technicians increased the steepness of the ramp and installed a steering robot in the test vehicle to induce a rollover. BM's commitment to safety leadership is evident in these advanced tests, which provide valuable data for the continuous development of advanced safety systems. BM's safety design incorporates high-strength and ultra-high-strength steel in strategic points of the vehicle, including the lower B-Paulo, doses, and reinforcement inside the doors. The X6 rollover sensor system utilizes front sensors to detect a frontal impact, pressure sensors in the doors to detect a side impact, and a rollover sensor to detect various types of rollovers. ADBUD JNIE is a leading manufacturer of professional touchless car washes, known for its high quality and reliable products. One of the key advantages of ADBUD JNIE's touchless car washes is that they are completely automated, making them easy to use and highly efficient. The touchless system eliminates the risk of damage to the vehicle surface, as there are no brushes or other physical contact with the car. This ensures that the car is cleaned thoroughly and effectively, without any risk of scratches or other types of damage. ADBUD JNIE also offers a wide range of chemicals and detergents specifically designed for touchless car washes. These chemicals are formulated to remove dirt, grime, and other types of debris from the car's surface, leaving it clean and shiny. The chemicals are safe for use on all types of vehicles, and are effective even at low concentrations, making them an economical choice for car wash operators. Welding automatic guided vehicles, AGVs, with advanced robotic systems is a complex and precise process. VOC Welding, a leader in robotic welding technology, demonstrates this with their sophisticated equipment and meticulous techniques. Phases of welding. The welding process is divided into several phases, each meticulously programmed and executed. Loading Phase 1. The first stage involves loading the initial components of the AGV onto the welding platform. The robot starts the welding process following the preset program. Unloading Phase 1. After completing the first set of welds, the partially welded AGV is unloaded to prepare for the next set of components. Loading Phase 2. The next set of components is loaded, and the welding process continues. Each phase is checked against the program to ensure accuracy. Checking adjustments. During each phase, the program's accuracy is verified, and adjustments are made if necessary. Cutting wire and touch sensing. The welding wire is cut to the desired length for touch sensing. The quick touch sensing technology then precisely aligns the welding seams. The video showcases the welding of AGVs, each weighing 18 tons, with a total welding length of 600 meters per vehicle. The Panasonic TA1900 WGH3 robot, mounted on an XYZ axis, is essential for reaching all welding points on these massive structures. Loading Phase 3. The final components are loaded for the last phase of welding. The robot completes the remaining welds, ensuring that the entire 600 meters of welding is flawlessly executed. Offline programming and DTPS software. A significant aspect of this welding process is the offline programming using DTPS, Desktop Programming and Simulation, software developed by VOC Welding. This software allows engineers to design and program the welding tasks without interrupting the production line. By simulating the welding process, the DTPS software helps in optimizing the welding parameters and sequences before actual implementation. This step is crucial for improving efficiency and reducing errors during the welding process. Advanced touch sensing and quality assurance. The extensive touch sensing sequences performed by the robot are pivotal for achieving high-quality welds. Quick touch sensing technology allows the robot to detect and correct any deviations in real time. This technology ensures that each weld is precise, minimizing the risk of defects and enhancing the overall durability of the AGVs. Welding of semi-trailer frames is a critical process in the manufacturing of durable and reliable transportation equipment. VOC Welding, in collaboration with its partners, has developed advanced robotic equipment for Kogel-Chosen to streamline this process. This state-of-the-art system automates the complete welding of semi-trailer frames, ensuring precision, efficiency, and consistency. The welding process begins with the initial assembly and tack welding of the frame. Tack welding is a preliminary step that temporarily holds the components together, ensuring they are correctly aligned for the final welds. Once the frame is tack welded, it is moved by a specialized carriage to an available workstation. This movement is part of a carefully coordinated logistical operation, ensuring minimal downtime and maximum throughput. The integration of robotics and automated logistics in this process not only improves production efficiency but also enhances the overall quality of the semi-trailer frames. This automated system developed by VOC Welding represents a significant advancement in the welding industry. By reducing human error and increasing the speed of production, it helps manufacturers meet high demand while maintaining stringent quality standards. The use of robotic welding in semi-trailer frame production exemplifies the ongoing trend towards automation and innovation in manufacturing, highlighting the benefits of integrating advanced technology in industrial processes. At the workstation, the frame is welded by 3 highly efficient welding robots. These robots are designed to perform precise and high-quality welds, which are crucial for the structural integrity of the semi-trailer frames. The use of multiple robots allows for simultaneous welding at different points of the frame, significantly speeding up the process compared to traditional manual welding. The robots are equipped with advanced sensors and control systems to adapt to variations in the frame and ensure uniform weld quality. After the welding is complete, the frame is transported once again by the carriage system to the output transfer point. From here, the welded frame is picked up for further processing, which may include additional assembly, painting, and quality inspections. Mechanical concrete tire-derived cylinders represent a revolutionary approach to road construction and repair. This innovative technology involves using discarded tire sidewalls to create thin-walled cylinders, which are then laid down as a base for roads. These cylinders are filled with aggregates such as number 57 gravel, offering a strong and stable foundation for roadways. One of the key advantages of mechanical concrete is its cost-effectiveness. Compared to traditional road construction methods, this approach can save up to 25% of the costs. This is because it requires less material, and there's no need for extensive compaction or water usage during installation. The resulting roads are durable and resistant to common issues like potholes and water damage. In practical applications, mechanical concrete has already proven its effectiveness. Roads built using this method have shown remarkable durability, even in high-traffic areas like the vicinity of power plants and ballparks. By repurposing old tires and reducing maintenance expenses, mechanical concrete presents an environmentally friendly and economically viable solution to road infrastructure challenges. Processing large mining and OTR, off-the-road, tires presents unique challenges due to their immense size and the often remote locations where they are stockpiled. CM Shredders, a leading company in the field, offers innovative solutions to efficiently handle these tires. One of the primary challenges when processing mining and OTR tires is their sheer size. These tires often have bead bundles measuring 4 to 6 inches in diameter, and when shredded whole, the thickness of the rubber doubles, requiring multiple cuts to handle the third dimension. CM Shredders addresses these challenges with patented knife and screening systems, ensuring the production of high-quality tire chips. CM chip shredders are versatile and capable of processing materials for size reduction, destruction, recycling, and more. They can be equipped with standard one-piece hook and shear knives or CM's patented replaceable insert knives. The unique feature of CM's patented knife technology allows knives to be sharpened and reused up to 6 times, significantly reducing operating costs. This feature also ensures the cleanest cut chips with minimal exposed steel wire. The cost of baling of tires, often handled by machines like the HSM 3521 horizontal baling press, is a crucial process in waste management and recycling. This equipment is designed to efficiently compress various materials, including tires, making them easier to handle, transport, and recycle. The HSM 3521 boasts an expansive loading aperture, allowing for the compression of large quantities of materials such as paper, cardboard, foils, packaging materials, and even foam. This versatility is essential in dealing with diverse waste streams. The hydraulic loading flap enhances operational comfort, while the hydraulic counterplate ensures safe and convenient bale removal. The process begins with manual loading of the materials into the baling press through the large opening. Once an adequate amount of material has been accumulated, the machine's stored program controller (PLC) signals that a bale is ready to be formed. Tire recycling is a critical aspect of sustainable waste management, environmental preservation, and resource conservation. As the global population continues to grow, so does the production of rubber products, including tires. Consequently, the volume of discarded tires and rubber waste has surged, leading to significant environmental challenges. However, innovative solutions like the radial tire shredding machine provided by Maxon India are playing a pivotal role in addressing these issues. In this section, we will delve into the importance of tire recycling solutions, focusing on the benefits of tire shredding machines and the recycling of rubber waste. The role of radial tire shredding machines. Radial tire shredding machines, like those offered by Maxon India, play a central role in the tire recycling process. These machines are designed to efficiently and effectively shred tires and rubber waste into smaller, manageable pieces. Here are some key reasons why these shredding machines are essential. Volume reduction. One of the primary objectives of tire shredding machines is to reduce the volume of rubber waste. By breaking down tires and rubber products into smaller particles, these machines make it easier to handle, transport, and store the material. Facilitate recycling. Shredded rubber waste is more amenable to recycling processes. The smaller particle size increases the surface area available for processing, enabling more efficient extraction of valuable materials such as rubber, steel, and textile fibers. Versatility. Radial tire shredding machines can handle a wide range of rubber waste, from car tires to industrial rubber products. Their versatility makes them a valuable asset for various industries and recycling facilities. Environmental benefits. By reducing the volume of rubber waste and enabling recycling, these machines contribute to reduced landfill usage and lower environmental pollution. This, in turn, supports a cleaner and more sustainable environment. Cost savings. Tire shredding machines can help businesses and recycling facilities reduce operational costs by streamlining waste management processes and maximizing the value of recycled materials. Understanding rubber waste. Rubber waste encompasses a wide range of discarded rubber-containing products and industrial waste materials. These materials can include old and used tires, car mats, fenders, shoe soles, industrial rubber parts, and various other rubber goods like packing materials, gaskets, and O-rings. Additionally, rubber waste may also comprise rejected or waste materials generated during the manufacturing processes of rubber products. Max in India's rubber and tire shredder offer a solution to reduce the volume of raw rubber waste by transforming it into small particles. This shredding process not only minimizes the volume of waste but also makes it more suitable for recycling purposes. Dry rubber waste is particularly valuable as it can be recycled to extract grease and lubricant oil used in machinery, as well as the vulcanized compound from the manufacturing process, which can be reprocessed and reformulated into new rubber products. Moreover, rubber waste has found applications in road construction, surfacing, and as a fuel source in cement factories. Why shredding and recycling rubber waste matters. Cost-effective recycling. Recovered rubber from shredded tire waste costs significantly less than natural or synthetic rubber. This cost-effectiveness makes it an attractive option for various industries, particularly those looking to reduce production costs. Enhanced properties. Recovered rubber often exhibits properties that are equal to or even better than those of virgin rubber. This makes it a valuable resource for manufacturing a wide range of products, from automotive parts to consumer goods. Energy efficiency. The production of rubber from reclaimed materials requires less energy compared to manufacturing rubber from virgin sources. This energy efficiency contributes to a reduced carbon footprint and lowers overall environmental impact. Effective disposal. Recycling through shredding offers an efficient and eco-friendly way to dispose of unwanted rubber products, which can be challenging to manage through traditional waste disposal methods. Conservation of resources. The recycling of rubber conserves non-renewable petroleum products, which are used in the production of synthetic rubbers. This resource conservation is essential for sustainable manufacturing and environmental protection. Job creation. Recycling activities in the rubber industry can generate employment opportunities, especially in developing countries. These jobs contribute to economic growth and poverty reduction. Diverse product range. Reused tires and other rubber products can be transformed into a wide array of useful items, such as playground surfaces, sports fields, shoe soles, and even fuel sources. Energy reclamation. Incinerating tires to recover embodied energy is another avenue for recycling rubber waste. This process yields substantial quantities of energy, further reducing waste and reliance on fossil fuels. Applications of recycled rubber. Recycled rubber from shredded tires and other rubber waste finds applications across numerous industries and products. Some of the notable applications include rubberized asphalt. Recycled rubber is often incorporated into asphalt mixes to create rubberized asphalt, which enhances road durability, reduces road noise, and improves skid resistance. Playground surfaces. Shredded rubber is commonly used as a safety surface material in playgrounds and sports facilities. It provides cushioning and reduces the risk of injuries from falls. Sports fields. Rubber infill made from recycled tires is used in synthetic turf sports fields. It enhances shock absorption, stability, and durability of the playing surface. Automotive products. Recycled rubber can be used in manufacturing automotive parts, such as gaskets, seals, and vibration dampening components. Footwear. Rubber waste is transformed into shoe soles and other footwear components, reducing the environmental impact of the shoe manufacturing industry. Construction materials. Shredded rubber can be used in various construction materials, including roofing materials, soundproofing products, and insulation. Agricultural use. Rubber mulch made from recycled tires can be used as a weed barrier and moisture retention layer in agriculture. Fuel source. Some industries use shredded rubber as a fuel source, particularly in cement factories and industrial boilers, where it serves as an alternative to fossil fuels. The welding of trailer chassis is a critical manufacturing process that requires precision, strength, and efficiency. To meet these demands, Turbos Hout in Belgium has implemented an advanced arc welding robot solution. This system, featuring a Panasonic TL2000 WGH welding robot, showcases the integration of cutting-edge technology to enhance productivity and quality in trailer chassis welding. The welding robot system. The Panasonic TL2000WGH is a state-of-the-art welding robot designed to perform precise and consistent welds. This robot is mounted on a gantry, providing it with the stability and range needed to handle large structures such as trailer chassis. The gantry itself is installed on a 16-meter track, allowing the robot to move along the length of the chassis and perform welds at various points with high accuracy. Quick touch sensing. One of the key features of this welding robot is its use of quick touch sensing. This technology allows the robot to detect the precise location and orientation of the parts to be welded. By using touch sensing, the robot can adjust its welding path in real time to ensure optimal contact and alignment. This capability is essential in welding operations where even minor misalignments can lead to weak joints or structural failures. Offline programming with DTPS. The programming of the Panasonic TL2000WGH is accomplished through DTPS, Desktop Programming and Simulation, offline programming software. This software enables engineers to create and simulate welding programs on a computer before implementing them on the robot. Offline programming offers several advantages. Efficiency. Engineers can develop and test programs without interrupting the production process. This minimizes downtime and increases overall productivity. Accuracy. Simulations allow for the detection and correction of potential issues before they arise on the shop floor. This leads to higher quality welds and fewer errors. Flexibility. Programs can be easily modified and optimized as needed, accommodating changes in production requirements or product design. Benefits of robotic welding for trailer chassis. The implementation of robotic welding for trailer chassis offers numerous benefits. Consistency. Robots can perform repetitive tasks with high precision and without fatigue, ensuring uniform weld quality across all chassis. Speed. Robotic systems can operate continuously and at higher speeds than manual welding, significantly boosting production rates. Safety. Welding is a hazardous task involving high temperatures, fumes, and the risk of electric shock. Robots mitigate these risks by taking on the dangerous aspects of the job, thus protecting human workers. Cost effectiveness. Despite the initial investment in robotic systems, the long-term savings from reduced labor costs, increased throughput, and lower defect rates make it a financially viable solution. Welding technology plays a critical role in modern shipbuilding, driving advancements in efficiency, structural integrity, and overall productivity. In an industry characterized by the need for large, complex, and highly durable structures, welding stands out as a cornerstone of construction and assembly processes. Firstly, welding ensures the structural integrity of ships. Given that ships are exposed to harsh marine environments, the joints and seams must withstand significant stress and strain. Welding processes, such as arc welding, MIG, metal inert gas welding, and TIG, tungsten inert gas welding, provide strong, durable bonds that are essential for the longevity and safety of ships. For instance, the tensile strength of welded joints can reach up to 70,000 psi, which is critical for the structural demands placed on ship components. Secondly, the efficiency of shipbuilding has dramatically improved due to advancements in welding automation and robotics. Automated welding systems can perform tasks with high precision and speed, reducing labor costs and minimizing human error. According to industry reports, the implementation of automated welding can increase production efficiency by up to 30%. This not only speeds up construction times but also ensures higher consistency and quality in welds. Additionally, welding technology has enabled the construction of larger and more complex vessels. With advanced techniques like electron beam welding and friction stir welding, shipbuilders can join thick metal plates and create intricate structures that were previously impossible. For example, friction stir welding allows for the joining of aluminum plates up to 50 millimeters thick without the need for filler materials, which is particularly useful in building lightweight but strong ship superstructures. The role of welding in ship maintenance and repair is also significant. Regular maintenance is crucial for the longevity and safety of ships, and welding is a primary method used for repairing hull damage and other structural issues. Welding allows for quick and effective repairs, often performed while ships are still afloat, minimizing downtime and operational disruption. In terms of environmental impact, modern welding techniques contribute to more sustainable shipbuilding practices. Processes such as laser welding and hybrid laser arc welding offer higher energy efficiency and reduced emissions compared to traditional welding methods. For instance, laser welding can be up to 90% efficient in terms of energy use, significantly lowering the carbon footprint of the shipbuilding process. Moreover, the global shipbuilding industry continues to grow, with projections indicating that the market will reach approximately $175 billion by 2025. This growth underscores the increasing demand for innovative welding solutions to meet the complex requirements of new ship designs, including those for cruise ships, container ships, and specialized vessels like LNG carriers.